All right, so now let's combine everything we've learned so far in this chapter to do some stoichiometric calculations. In this example, I want us to combust propane gas in oxygen. Propane is a hydrocarbon fuel, and it has the formula C3H8. So when I say combustion in oxygen, what I'm talking about is burning in oxygen. And one big hint that you need for combustion problems is to know that whenever you combust a hydrocarbon is just any molecule that contains only carbon and hydrogen. That means combustion means that you're reacting the hydrocarbon with oxygen, O2 gas, and the products are always going to be water and carbon dioxide. So whenever you do combustion, the products are always the same. So this is going to be C3H8 gas plus oxygen gas to produce H2O and CO2. Now, I wasn't told what phase the water is, but it's pretty safe to assume in a combustion reaction that whatever is coming out of your tailpipe or whatever is going to be a gas. So here, this is my unbalanced reaction for the combustion of propane. And again, whenever you combust a hydrocarbon, the products are always going to be H2O and CO2. We have to figure out how to balance this reaction. So looking at the most complicated molecule, C3H8, I'm going to need 3 carbons. So I'm going to stick a 3 here to bring the carbons into balance. And I have 8 oxygens on the left. So I'm going to stick a 4 here to bring the hydrogens into balance. Now I have 3 times 2 is 6 plus 4 is 10 oxygens on the right. So if I stick a 5 here, I can bring the oxygens into balance. So now I have my balanced equation for the combustion of propane. Now, balancing the equation is crucial because the coefficients of a balanced chemical equation, so these stoichiometric coefficients, it would be 1, the 1 is implied here, to 5, to 4, to 3. Those represent the relative number of moles of reactants and products. Or even you could say the relative number of molecules that are reacting. So what this means is that if we take the balanced chemical equation and we look at it, we can tell the relative proportions of the reactants and products to each other. So this balanced chemical equation for the combustion of propane is really telling me that 1 mole of propane produces 3 moles of carbon dioxide and 4 moles of H2O. So I have this quantitative relationship. I could also say, I call it moles, but equivalently, a molecule of propane produces, 1 molecule of propane produces 3 molecules of carbon dioxide and 4 molecules of water. I can also say it in various ways, right? I could say that 5 moles of O2 are going to produce 4 moles of H2O, et cetera, et cetera, et cetera. We have this kind of quantitative ratio that's given by the balanced equation. So now, given that balanced equation, we can figure out a whole lot about the chemical reaction. For example, how many moles of O2 are required to react with 0.20 moles of propane? So I can approach this using dimensional analysis. If I have 0.2 moles of propane, then I can look at that chemical equation, and from that balanced chemical equation, from those stoichiometric coefficients, I can see that I have a 5-to-1 ratio of oxygen to propane. So that means that I can take that ratio and say I have 5 moles of O2 for every 1 mole of C3H8. And again, these are just from the stoichiometric coefficients. 0.2 times 5 is going to give me 1 mole of oxygen. And you can see how I'm able to cancel out the moles of propane here. So let's do it again. Let's do another example. How many moles of carbon dioxide can be produced from 0.75 moles of oxygen? We can approach it in exactly the same way using the relationship, the stoichiometric relationship of CO2 to oxygen. I have 0.75 moles of oxygen, and the ratio of carbon dioxide to oxygen is given by the balanced chemical equation. So I can see that I have 3 moles of carbon dioxide for every 5 moles of oxygen. So I can plug that ratio in, 3 moles of CO2 for every 5 moles of oxygen. And now I can cross out the moles of oxygen, cancel the moles of oxygen, and I'm left with 0.75 times 3 divided by 5 is 0.45 moles of CO2 that are produced in that reaction. So let's add a layer of complexity to this. I've been asking you about moles thus far, but can we see how many grams of oxygen are required to produce 5 grams of water? Careful here, okay? So a very important point to make here is that masses in grams do not represent the number of molecules or the number of moles reacting. In order to solve a stoichiometric problem like this, you have to convert from grams to moles. You have to convert the masses to moles using the molecular weight of whatever compound you're talking about. Okay, if you don't do that, you get into really big trouble. So I want to produce 5 grams of H2O. So I need to convert that to moles of water. So I need to use the molecular weight of water, which I can calculate from the periodic table. It's 18.02 grams. So I have 18.02 grams of water per mole of water. And that will enable me to cancel out the grams of water. Okay, but I also want to convert water to oxygen. So looking at the balanced chemical equation, I have 5 moles of oxygen for every 4 moles of water. And the final step would be, because I want grams of oxygen, I'm going to need to use the molecular weight of O2. So 16 plus 16 is 32 grams of O2 per mole of O2. So if I do all of that, I am able to cancel moles of water, cancel moles of oxygen, and I'm left with exactly what I wanted, which is the grams of oxygen. So this calculation should give me about 11 grams of oxygen. So remember that you must always convert grams to moles if you want to do stoichiometric calculations from balanced chemistry.